Welcome to our exploration of communication systems. In today's interconnected world, understanding how information travels from one place to another is more important than ever. Communication systems are the backbone of modern society, enabling everything from simple phone calls to complex data transfers across the globe. In this video, we'll break down the essential concepts, starting with what a communication system is, and gradually moving through its key elements, types of signals, and the technologies that make it all possible. Let's dive in and discover the fascinating world of communication systems together. Communication system is a set of components and processes that work together to transfer information from one place to another. Whether it's a conversation between two people, a radio broadcast, or a text message sent across continents, all these rely on communication systems. The main goal is to ensure that the message sent by the sender is accurately received by the receiver, despite any obstacles or interference along the way. This process involves encoding, transmitting, and decoding information, making communication systems a vital part of our daily lives. Every communication system is built from a few fundamental elements. These include the information source, transmitter, channel, receiver, and destination. The information source generates the message, which is then converted into a signal by the transmitter. The channel is the medium through which the signal travels, and it can be anything from a wire to the air itself. The receiver captures the signal and converts it back into a message for the destination. Understanding these elements helps us appreciate how messages travel seamlessly across vast distances. Communication systems, a signal is a physical quantity that carries information. Signals can take many forms, such as electrical voltages, light pulses, or sound waves. They are the means by which information is encoded and transmitted from the sender to the receiver. Without signals, there would be no way to transfer messages over distances. Signals are the lifeblood of communication, making it possible for us to share ideas, data, and emotions across the world. Signals can be classified into two main types, analog and digital. Analog signals are continuous and can take any value within a range, like the smooth flow of a wave. Digital signals, on the other hand, are discrete, taking only specific values, usually represented by zeros and ones. Analog signals are often used in traditional radio and audio transmissions, while digital signals are the foundation of modern computing and telecommunications. Understanding the difference between these two types is crucial for grasping how various communication technologies work. Modulation is a key process in communication systems. It involves altering a carrier signal in order to encode the information that needs to be transmitted. By changing certain properties of the carrier, such as its amplitude, frequency, or phase, we can embed the message onto it. Modulation makes it possible to send signals over long distances without significant loss or interference, ensuring that the information reaches its intended destination clearly and efficiently. You might wonder why modulation is necessary in the first place. The main reason is that raw signals, like human voice or data, often can't travel long distances effectively. Modulation allows these signals to be transmitted over various media, such as radio waves or cables, by adapting them to frequencies that can travel farther and with less interference. This process also enables multiple signals to share the same channel without mixing up, making communication more efficient and reliable. Amplitude modulation, or AM, is one of the earliest and most widely used modulation techniques. In AM, the amplitude of the carrier signal is varied in proportion to the information being sent. This method is commonly used in radio broadcasting, where audio signals are transmitted over long distances. While AM is simple and effective, it can be more susceptible to noise and interference compared to other modulation methods. Frequency modulation, or FM, is another popular technique where the frequency of the carrier signal is varied according to the information signal. FM is widely used in radio broadcasting, especially for music and high-fidelity audio, because it offers better resistance to noise and interference than AM. This makes FM ideal for delivering clear and consistent sound quality over the airwaves. Phase modulation, or PM, is a technique where the phase of the carrier signal is changed in accordance with the information signal. PM is closely related to FM and is used in various digital communication systems. It provides certain advantages in terms of bandwidth efficiency and is often used in combination with other modulation methods to achieve reliable data transmission. Modulation is the reverse process of modulation. It involves extracting the original information signal from the modulated carrier at the receiver's end. Without demodulation, the transmitted message would remain hidden within the carrier signal and be unintelligible to the receiver. Demodulation is a crucial step in ensuring that the information sent by the transmitter is accurately recovered and understood by the recipient. Block diagram is a simplified representation of a communication system, showing its main components and how they interact. Typically, it includes the information source, transmitter, channel, receiver, and destination. Each block represents a specific function, making it easier to understand the flow of information from sender to receiver. Block diagrams are essential tools for engineers and students alike, helping visualize and analyze the structure of communication systems. Bandwidth refers to the range of frequencies that a signal occupies. It determines how much information can be transmitted in a given amount of time. The greater the bandwidth, the more data can be sent, which is why high-bandwidth channels are essential for modern applications like video streaming and online gaming. Understanding bandwidth helps us appreciate the limitations and possibilities of different communication systems. Noise is any unwanted disturbance that interferes with the transmission and reception of signals. It can come from various sources, such as electrical equipment, atmospheric conditions, or even other communication systems. Noise can distort or weaken the signal, making it harder for the receiver to accurately interpret the message. Reducing noise is a major challenge in designing effective communication systems. Propagation refers to how electromagnetic waves travel from the transmitter to the receiver. These waves can move through different media, such as air, vacuum, or even solid objects. The way they propagate depends on factors like frequency, obstacles, and atmospheric conditions. Understanding propagation is key to designing systems that can reliably transmit signals over long distances. Ground wave propagation occurs when radio waves travel along the surface of the Earth. This type of propagation is commonly used for AM radio broadcasts, especially over short to medium distances. Ground waves can follow the curvature of the Earth, making them ideal for reaching receivers that are not in direct line of sight with the transmitter. However, their range is limited by the Earth's conductivity and terrain. Skywave propagation involves radio waves being reflected back to Earth by the ionosphere, a layer of the atmosphere. This allows signals to travel over much greater distances than ground waves, making it possible to communicate across continents. Skywave propagation is especially important for shortwave radio and international broadcasts, but it can be affected by atmospheric conditions and solar activity. Space wave propagation occurs when radio waves travel directly from the transmitter to the receiver through the atmosphere. This method is used for line-of-sight communications, such as television broadcasts, satellite links, and microwave transmissions. Space waves are ideal for high-frequency signals and are less affected by the Earth's surface or atmospheric layers, making them reliable for modern communication systems. Satellite communication uses artificial satellites orbiting the Earth to relay signals between distant locations. This technology enables global broadcasting, internet access, and telephone services, even in remote areas. Satellites act as relay stations, receiving signals from one location and transmitting them to another, overcoming the limitations of ground-based systems. Satellite communication has revolutionized the way we connect across the world. Optical fiber communication uses thin strands of glass or plastic to transmit data as pulses of light. This method offers extremely high bandwidth and low signal loss, making it ideal for internet, telephone, and television services. Optical fibers are immune to electromagnetic interference and can carry vast amounts of data over long distances, forming the backbone of modern communication networks. Communication technology is essential in modern life. It connects people, businesses, and governments, enabling the rapid exchange of information and ideas. From social media to emergency services, communication technology underpins almost every aspect of our daily routines. It drives economic growth, fosters innovation, and helps bridge cultural and geographical divides, making the world a smaller and more connected place. Information source is where the message originates in a communication system. It could be a person speaking, a computer sending data, or a sensor collecting measurements. The quality and clarity of the information source directly impact the effectiveness of the entire communication process. Ensuring a reliable and accurate source is the first step toward successful communication. The transmitter is responsible for converting the original message into a signal suitable for transmission. This involves encoding the information and modulating it onto a carrier wave. The transmitter ensures that the signal is strong enough to travel through the chosen channel, whether it's a wire, fiber optic cable, or the air. A well-designed transmitter is crucial for minimizing loss and distortion. The channel is the medium through which the signal travels from the transmitter to the receiver. It can be physical, like a cable or optical fiber, or wireless, like radio waves in the air. The choice of channel affects the speed, quality, and reliability of communication. Channels can introduce noise and distortion, so selecting the right one is vital for effective transmission. Receiver's job is to capture the transmitted signal and convert it back into a form that the destination can understand. This involves demodulation and decoding. The destination is the final point where the message is delivered, such as a person's ear, a computer, or a display screen. Together, the receiver and destination complete the communication process, ensuring the message reaches its intended audience. Encoding is the process of converting information into a signal that can be transmitted, while decoding is the reverse process at the receiver's end. These steps are essential for ensuring that the message remains intact and understandable throughout its journey. Effective encoding and decoding techniques help protect against errors and loss of information. Channels come in many forms, each with its own advantages and limitations. Wired channels, like copper cables and optical fibers, offer high reliability and security. Wireless channels, such as radio waves and microwaves, provide flexibility and mobility. The choice of channel depends on factors like distance, bandwidth requirements, and environmental conditions. Analog signals are found in many everyday applications. Examples include audio signals from microphones, video signals in traditional television, and temperature readings from analog sensors. These signals vary smoothly over time and can represent a wide range of values, making them suitable for natural phenomena and continuous data. Digital signals are everywhere in modern technology. Examples include computer data, digital audio and video, and signals used in smartphones and the internet. These signals use discrete values, typically zeros and ones, allowing for easy processing, storage, and error correction. Digital signals are the foundation of today's information age. Analog signals are simple to generate and process, making them ideal for applications like audio broadcasting and analog telephony. They can represent natural phenomena accurately and are less affected by quantization errors. However, analog signals are more susceptible to noise and distortion, which can degrade quality over long distances. Digital signals offer many benefits, including high noise immunity, easy error detection and correction, and efficient storage and transmission. They enable advanced technologies like digital television, internet, and mobile communications. Digital signals can be compressed and encrypted, providing security and saving bandwidth. Despite their simplicity, analog signals have some drawbacks. They are prone to noise, distortion, and signal degradation over long distances. Analog systems also have limited capacity for error correction, making them less suitable for modern, high-speed communication needs. Digital signals, while powerful, also have limitations. They require complex processing and conversion equipment, and quantization errors can occur during analog-to-digital conversion. Additionally, digital systems can be more expensive to implement, especially in areas with limited infrastructure. There are several types of modulation, each suited to different applications. The main types are amplitude modulation, AM, frequency modulation, FM, and phase modulation, PM. Each method alters a different property of the carrier signal to encode information, offering unique advantages and trade-offs in terms of bandwidth, noise resistance, and complexity. Amplitude modulation is widely used in AM radio broadcasting, aviation communication, and two-way radios. Its simplicity and ease of implementation make it suitable for applications where cost and coverage are more important than sound quality. However, AM is more vulnerable to noise and interference compared to other methods. Frequency modulation is the standard for FM radio, television sound, and high-fidelity audio systems. Its resistance to noise and ability to deliver clear sound make it ideal for music and entertainment broadcasting. FM is also used in radar and telemetry systems, where signal integrity is crucial. Phase modulation is used in digital data transmission, such as Wi-Fi, Bluetooth, and satellite communication. Its ability to efficiently use bandwidth and resist certain types of interference makes it valuable in modern wireless networks. PM is often combined with other modulation techniques for enhanced performance. Multiplexing is a technique that allows multiple signals to share the same communication channel. This is achieved by combining several signals into one, transmitting them together, and then separating them at the receiver's end. Multiplexing increases the efficiency of communication systems and is essential for modern networks like telephone exchanges and internet data transmission. Noise in communication systems can be classified into several types, including thermal noise, intermodulation noise, and crosstalk. Each type has different sources and effects on signal quality. Understanding the nature of noise helps engineers design systems that minimize its impact and ensure reliable communication. Reducing noise is a major goal in communication system design. Techniques include shielding cables, using error correction codes, and selecting appropriate frequencies. Advances in digital technology have made it easier to detect and correct errors, further improving the reliability of modern communication systems. The electromagnetic spectrum encompasses all possible frequencies of electromagnetic waves, from radio waves to gamma rays. Communication systems use specific parts of this spectrum, such as radio, microwave, and infrared frequencies, to transmit information. Efficient use of the spectrum is essential for avoiding interference and maximizing capacity. Repeaters are devices that receive, amplify, and retransmit signals to extend their range. They are commonly used in long-distance communication systems, such as telephone lines and optical fiber networks. Repeaters help overcome signal loss and ensure that messages reach their destination clearly, even over vast distances. Wireless communication uses electromagnetic waves to transmit information without physical connections. Examples include radio, television, mobile phones, and Wi-Fi. Wireless systems offer flexibility and mobility, making them essential for modern lifestyles and business operations. Wired communication relies on physical connections, such as copper cables and optical fibers, to transmit signals. These systems offer high reliability, security, and speed, making them ideal for critical applications like internet backbones and data centers. Wired communication remains a cornerstone of global connectivity. Future of communication systems is bright, with ongoing advancements in technology promising faster, more reliable, and more secure connections. Innovations like 5G, quantum communication, and the Internet of Things are set to transform the way we interact and share information. As communication systems evolve, they will continue to shape our world, making it more connected and accessible than ever before.